So we've looked at anthracene, it's the synthesis of anthracene, as well as the synthesis of some derivatives of anthracene. So this session is solely going to look at phenanthrene. So at the end of the session, you should be able to describe the general method for the preparation of phenanthrene. You should be able to describe the synthesis of substituted phenanthrene, and lastly, you should be able to prepare phenanthrene using the Badhan-Sengupta synthesis. So the first synthesis route we will look at is the general method for the synthesis of phenanthrene. Now, the Howard succinic anhydride synthesis is used starting from naphthalene. So, just like in anthracene, in phenanthrene too, naphthalene is a key precursor in the synthesis of phenanthrene. And in this general method, the preparation of this phenanthrene from naphthalene involves a series of steps, including a Feathercraft acylation and 2-Clemenson reduction. So through this Feathercraft acylation with the succinic anhydride, it can lead to the formation of two products where the succinic anhydride attaches itself to either carbon number 1 or carbon number 2, right? And afterwards, then the ring closure goes on, leading to the formation of phenanthrene. So let's please look at the two different routes. So with route A, the Clemenson reduction goes on to produce this intermediate, which is slightly different from this intermediate because the carboxylic acid chain is attached to two different parts of the naphthalene ring. But however, it leads to the formation of the same product, and this product is known as the keto 1,2,3,4 tetrahydrophenanthrene. So this next slide simply looks at the mechanism of action for the attack at carbon number 1. So the Clemenson reduction goes on. There's the acid hydrolysis leading to the ring closure. There's the reduction leading to our final fused 3-membered ring, which one is not an aromatic. So reduction with selenium is what eventually leads to our final product phenanthrene with the 3 fused benzene rings intact. So the next synthesis route we'll be looking at is the Badhan-Sengupta phenanthrene synthesis. Now, two key steps are involved in this reaction. The first one, there is the electrophilic aromatic substitution using a tethered cyclohexanol group as well as diphosphorus pentaoxide, which closes the central ring onto an existing aromatic ring. So that is seen here. So this is the first step by the use of the diphosphorus pentaoxide to yield our first intermediate. Now this intermediate undergoes another reaction, which is oxidation using elemental selenium to convert the other two rings into aromatic rings. Okay, so next is to look at the Score synthesis of phenanthrene. Now in this synthesis, there is the heating of O-nitrobenzaldehyde with sodium phenyl acetate in the presence of acetic anhydride to give an intermediate product. And this is the intermediate product. So our O-nitrobenzaldehyde reacts with sodium phenyl acetate in the presence of acetic anhydride to produce an intermediate. Now this resultant intermediate is reduced and diazotized from diazonium salt, which is treated with concentrated acid and copper to produce the 9-phenanthrene carboxylic acid. Now this 9-phenanthrene carboxylic acid is then heated to remove carbon dioxide, yielding our final product, which is the phenanthrene. So this is also another synthesis of phenanthrene together with the first one we discussed. Now lastly, in this session we are going to look at the synthesis of substituted phenanthrene. So substituted phenanthrene can be obtained using this intermediate, the the keto 1, 2, 3, 4 tetrahydrophenanthrene can be used in the synthesis of some substituted um, phenanthrene products. So here we react our keto 1, 2, 3, 4 tetrahydrophenanthrene, which was the intermediate in the product formed in the other general synthesis of phenanthrene using the succinic anhydride. In this particular synthesis, we can use that intermediate to synthesize other derivatives, other substituted derivatives through the reaction with alkyl lithium compounds followed by the hydrolysis in acid or water to produce our substituted phenanthrene.